All right, so this is another important article that I'm going to be explaining in this video. And the concept of steerability of equivariant neural networks, the definition changes from one article to the other, but this article historically is more essential. Of course, different researchers have different definition of what is a steerable CNN, but let's focus on this important article. So it has long been recognized that the invariance and equivariance properties of a representation are critically important for success in many vision tasks. In this paper, we present a steerable convolutional neural network, an efficient and flexible class of equivariant convolutional network. But some authors say the opposite. For example, they say a generalization of equivariant convolutional neural networks is a steerable CNN. But this article is saying it differently. We show that steerable CNNs achieve state-of-the-art results on CFAR images classification benchmark. The mathematical theory of steerable representations reveals a type system in which any steerable representation is a composition of elementary feature types, each one associated with a particular kind of symmetry. Of course, all of these definitions of steerability share the same idea that it's a composition of elementary feature types. Later, you'll see that, for example, for different kernel, for example, if you rotate it again. If you rotate it, you have, for example, k filters, k rotations. Then you will see that under your feature space, it's like permuting it. It becomes another theta, another angle. For example, theta is equal to 0, 30, and then you will see that the group becomes a permutation of the features that are, and so it's like this group that we are talking about. So in deep learning, however, intermediate layers should not be fully invariant because the relative pose of local features must be preserved for further layers. Thus, one is led to the idea of equivariance. A network is equivariant if the representations it produces transform in a predictable linear manner under the transformation of input. In other words, equivariant networks produce representations that are steerable. Steerability makes it possible to apply filters not just in every position, but in every pose, thus allowing for increased parameter sharing. So, for example, that this 2D signal, and so we have k channels. For example, for any x and y, we have intensity for each of the channels of green, red, and blue, GRB. Different level of intensity for each point. So this is we call it as feature map. And then it is customary in deep learning to describe F as a stack of feature maps because we usually have k channels. We have k channels. Each channel could be a different kernel that is learning, for example, different rotations or reflections or anything else. In this paper, we also consider another decomposition of fibers, of F into fibers. The fiber at position x in the base is the k-dimensional vector space that spans all channels at a given position. Of course, there is an interesting paper called misuse or using or misusing equivariant neural networks, it is saying that sometimes we have redundancy in all of these features. We have k channels. It means that you have k feature maps. You should take the correlation so that if they are very correlated to each other, then they are redundant. Given some group of transformations that acts on points in Z2, we can transform signals like this. So this says that the pixel G minus X gets moved to X. So we are in this pixel G minus X. It moves to X by some transformation, for example, rotation. So G is G of rotation, just 1 degree, for example, 30 degree. So G of 30, let's say. So we know that pi 0 G is a linear operator. An important property of pi 0 is that pi 0 of GH is pi 0 of 0, pi 0 of GH. So GH means composition of transformations in G. For example, if you rotate 30 degree, then rotate 20 degree, it becomes 50 degree. So a vector space such that F0 equipped with a set of linear operators satisfying this condition is known as group representation. I think in this paper they didn't write like that. But for myself, I always do this representation. We want to represent this group by some matrices. Rn, for example, all matrices that, because if we map them to the space of matrices on a vector space, usually on Rn, then we can, this decomposition that in this space could be reflected in this space. So we can understand our group by understanding our matrices. And of course, we have a reducible representation, irreducible regular representation, and a trivial representation. And this is important. This diagram shows the structural consistency that follows from equivariance of the network phi and the group representation structure pi 0. So if you, for example, rotate it by R, then M, it's like become MR. It's like first you rotate it and then do the nonlinear map, or then first you do nonlinear map and then do translated. These transformation, group transformation, both of them should coincide. So this path should produce the same result as this path. A filter bank can be described as any array of dimension where K and K prime denote the number of input-output channels and S is the kernel size. For our purposes, it is useful to think of a filter bank as a linear map that takes as input a signal and produces a K prime dimensional feature vector. The filter bank only looks, of course this definition is for each pixel. For each pixel, you have a vector that for each of them, each entry is for one channel. So we assume that we have a representation that allows us to steer F. In order to make the output of the convolution steerable, we need the filter bank to be edge equivariant. So if you do this psi and then permute it, it's like doing the rotation and then use this nonlinearity. So this filter bank psi is H equivariant. So in this example, rho 1 represents the 90-degree rotation by R. Rotation R by permutation matrix that cyclically shifts in the 4 channels. As you see, we have these 4 channels, 1, 2, 3, 4. Now if you shift it, for example, it becomes 4, 3, 1, 4, 1, 2, 3. It's like permutation. So we have shown how to parameterize filter banks that intervene pi and rho, making the output fibers steerable by rho. So we say the output fibers is steerable by rho. This happened through a natural important construction known as induced representation. So the correlation psi f, we are doing correlation here. When you do psi on f, we get the correlation. We are doing correlation operator, then we get this feature vector. So the correlation could be computed by translating f before applying psi. So before applying psi, we can just rotate it and then apply the convolution. Then it's like permuting what you have obtained. So we can now calculate the transformation law of the output space. So this coincides. And a group representation is a set of invertible linear maps satisfying that rho for all elements. And it can be shown that any representation is a direct sum of a number of elementary elementary representations associated with G. And these building blocks, EI, for example, we have M building blocks. These EIs are called irreducible because, for example, if E1, E2, E3, we have this representation, then we cannot reduce E1 further to say that E11, E1, E22. We cannot represent like that. We cannot reduce like that. And so this is irreducible representation. We have these irreducible representations. So this group is generated by 90-degree rotations and mirror reflection M. M is mirror reflection, and has it has five irreducible representation labeled A1, A2, B1, B2. Because sometimes you just want to mirror, sometimes we want to rotate it, but if you combine them, then it becomes a general transformation. And this character is very important, the trace of your representation. And the rest of that is just theoretical things. This regular representation is very important. Because now the feature maps are thought of as functions. Instead of function on plane, we have from group to RK. Instead of from plane to RK, now we have from group to RK. This is more general. So it's a regular representation. It is easy to see that a regular representation is naturally realized by permutation matrices. Of course, if you look at Wikipedia, the definition of a regular representation is like mapping to itself. For example, left multiplication, it means that when you multiply H, for example, to the left of your group, then it's left invariant. So it's like you don't change it, but you just permute it. So this coset space carries a natural left action by H, and this allows you to create this quotient space. So the H action permutes these values because it permutes cosets. So rho can be realized by permutation matrices. So you saw there that we had rho. That rho is permutation matrices. It was here, in this slide. So if you just permute it, that's why we are talking about these H representations. We decompose them because this action translates into action on the space of functions on H and K. So Q denotes the space of functions. Then we have the following representations. The H action permutes these values because it permutes cosets. Hence, rho can be realized by permutation matrices. For small groups, the explicit computation can easily be done by hand, while for large groups, this task can be automated. In this way, we get one permutation representation of each subgroup. So for a trivial, subgroup, it becomes itself. The representation in the space of functions is known as regular representation. Using such regular representation in a steerable CNN is equivalent to using group convolution introduced in 2016. So steerable CNN are a strict generalization of so all the papers are saying this steerable is just a generalization of group convolutional neural networks. That's true. Many papers have noticed this. So we have these subgroups, the quotient, feature name, and the dimensionality of each of them.